I gave you the article in BBC, and the idea is that, and this is one of my favorites because I've given presentations on calendars before and on time itself. But basically, and I'm going to ask you guys because I like an interactive audience, is essentially how did we tell time, 200 years ago? Here's from the article itself. How did we tell time? Let me make sure the audience is awake out there. Okay. Anybody? I gave you the answer there, but okay, you can use voice. We don't want too many people using voice because we can because I don't have any cues about when you're talking, but if you would like to use voice, please. Maybe you can tell me why we used the sun, why we didn't use a clock or something. Or when did we need clocks? Okay, Raja? Herman? Okay, yeah, Romans had water clocks. A lot of people had water clocks. They used, why would you even need a clock? How accurate did time have to be is what I'm really getting at. Yeah, okay, so time did not have to be very accurate. Basically, for a lot of people, they woke up, hey, when the sun came up, or since they went to bed early, they probably woke up before the sun. They got busy doing things. If there was any coordination at all, where did they probably get it from? In other words, what indicated time in most cities and still does? If you look at the heart of most cities in Europe or other places, what do you find? Yeah, okay. Church bells or a big clock in the town square, right? Okay, so seasons, yes. Why seasons? Because the only reason we need calendars back at that time was for a couple reasons. One was agricultural, where you planted and you reaped the harvest, and the other was for religious or secular reasons. Now, navigation is another one. Maria just brought up an interesting thing about navigation. Obviously, if you are going to keep track of longitude, there's an entire, yes, meridians. If you were going to keep track of longitude, there's an entire contest back in the 1700s for who could make a clock that would be usable on board a ship. Remember, ships move, and so pendulum clocks would have to be, couldn't work on a ship quite as well, and there was a big prize for being able to tell time because that was the only way you could tell longitude. Latitude was easier, of course, because you had the sun. Okay, so why did we need more accurate clocks? At what time did we need more accurate clocks? For you guys in the UK, this is particularly applicable. What was it about the UK? What was going on in the early 1800s? What technology came into play? Trains, yes, Herman. Trains in the early 1800s. What about trains? What was the fastest speed that people could travel up till trains? Anybody out there? You could run. What was faster? Trains went with the time of the city. Okay, yes, okay. For humans, bullets, okay, but you can't ride a bullet. What can you ride? What goes faster than the human running? Horses. Okay, that's the answer. So horses, wagons, etc. So the speed of horse, not the speed of light, not the speed of sound, but the speed of horse was the fastest speed that you could go up until we had trains. In fact, it was the fastest speed of communication. There were a lot of battles that were fought after treaties were already signed because they couldn't get it. I know for the United States, the War of 1812, there was a battle in New Orleans that was fought after the treaty was already signed because it was too far to get the message to the players. Yep. Oops, especially for the people there. Now, Pony Express actually only in the United States was one thing they tried. In other words, how do you get people to go faster on a horse? Well, you go really, really fast on the horse, get off, get another horse, go really, really fast. That was about leading edge communications technology, and it really only lasted 3 years because now if I am speaking, I understand there are a lot of people in the audience who English is not their first language. I tend to speak a little bit quickly. If I do, please let me know. I don't want to. I want to share, and I don't with the article, and I don't want to speak too quickly. So, yeah, Pony Express only lasted 3 years because in 1840 we had the telegraph. All of a sudden, communications was the speed of light, and you could send a message across the country. You could send a message across to continents after the transatlantic cables were laid in the 1870s, I believe. Here again, I'm tapping into things, knowledge that from. But in going back into the article, what would happen if you did not have accurate timetables for trains? What were some of the things that actually happened? Here again, if you want to follow along, I'm looking at a very fascinating BBC article, which I think is one of the best ones explaining time, and in a practical way, why we need things like cesium clocks. Okay, well, here's one instance. For example, if you did not have time, one of the things was not only missing your train, perhaps, what about train crashes? If one train had one time and another train had another, they might be on the track at the same time. This was somewhat catastrophic. So in the UK, you had in early 1840, you had what was called railway time. Anybody in Mexico? You don't have to answer, but yeah, bidirectional shared tracks plus the need for downtime. Yes. Anybody in Mexico out there? You don't have to actually answer. That's one of the cardinal rules of Second Life, is not sharing things you don't want to share. But it was not until too long ago that the time zones in Mexico were known as railway time, and it was because of this need for a central time. So back at that time, they decided in the UK in the 1840s to time their day by the Royal Observatory in Greenwich. And we still do that today. Does anybody, by the way, know what the first city for universal time was? It was not Greenwich. By universal time here, I'm talking about UT. It wasn't London, actually. There was one time where they tried it in a different city. Anybody guess what city that might be? In fact, it was actually in a book. It was on the book about, oh, now I can't remember. One of the ones with, okay. It was Paris. And they actually have a meridian there also. Okay, so does anybody know when we had universal time? This one was not in the article, but I happen to know that. UT, or universal time, was proposed by, I'm trying to write and speak at the same time, was proposed by a Canadian railway worker who decided that to go ahead and keep UT time, obviously, because of the Canada attached to the Commonwealth, and so they decided to keep the Greenwich system. And why is it needed? Why is universal time needed? Okay, to coordinate, obviously, yes, absolutely, coordinate. And here again, for railways to go across continents, between countries, all of this. Now, it didn't become quite so important until later on. Does anybody know how GPS works? Yeah, okay, so GPS GPS works with very precise time differences between the signal from your device, like your cell phone, up to the satellite and back. Now it's kind of triangulated. Now nuclear clocks, we're talking about cesium here. So before nuclear clocks, and does anybody know what was before cesium clocks? In fact, I just put it up on the board there. I mean, excuse me, not the board. Up on the chat is that the quartz clock. Now, what about quartz for you guys that are out there? What about quartz? Why are we talking about quartz and cesium and all that good stuff? How do they tell time? How do we use them to tell time? Yeah, quartz, like on a wristwatch, absolutely. That was, as I put up there, a physicist named Louis Asson developed the first quartz ring clock. Vibrations, absolutely. That's correct. So we could actually time the vibrations. We had technology to time the number of vibrations of quartz. I don't remember what the number of vibrations in quartz, but in cesium, it was able to be timed by the resonance of it. And quartz here, let me see. Okay, so cesium has a very high frequency rate, and so we were able to time clocks. Here again, if you look at the chat, you'll see that the cesium atom frequency, resonance frequency, and here again, this is the frequency of electrons jumping from one energy level to another, is precisely 9,192,630 or 9,192,631,770 hertz. Wow, to be precise. Now, obviously, you can't time it, but we had technology that was leading edge at the time. There is a picture in the article. Here again, for anybody that showed up, the article I'm looking at is this wonderful one from BBC. And they were able to, with these, so why would you want a cesium atom or whatever to be able to time their frequencies? What types of applications? And how accurate was it? I mean, if you had a watch, how accurate are watches? Yes. Well, why can't we just use the sun, okay, or the moon or anything else? Yeah, the moon actually, because one of the things is because the orbit of the sun is not circular, right? So actually, anybody know laws of physics there? Yes. So if you have an elliptical orbit, it's going to, there's also a wobble, very, very large earthquakes and other things actually change the day, the length of day by millionths of a second. The tides, I mean, it's really very unreliable as far as if you're getting down to parts of a second. Now, here's something from the article, is that the quartz watch would only err 1 second every, Kepler's laws, absolutely. In fact, I'm showing my, I got to remember, I don't do physics all the time, I do computers, but which law is it? Anybody out there? Somebody's got to know about which Kepler's law. But in any case, the quartz watch had an accuracy of 1 second in 3 years, but the atomic clock, which was created by the National Physical Laboratory in 1955, was accurate to 1 second in 1.4 million years. So, getting back to GPS, the only reason we're able to use GPS is because each of the little GPS satellites has a cesium clock in it, and it's able to coordinate with each other and be able to tell time extremely accurately, so that we're able to triangulate where we are in location. Okay, so is there anything better than a cesium clock? And that was kind of the gist of the article. Oh, yeah, okay. First ellipse, second speed along the orbit based on, exactly. Okay. Yeah, Earth science. Okay, what do you mean by nuclear clock, 8-bit? Yeah, okay. Essentially, when we say nuclear, we mean atomic. In this case, it may not be the nucleus of the atom itself, but in this case, cesium, it's the electron that's able to shift from one orbit to another. And so that may be what um, we've come to know as a nuclear clock. Now, the interesting thing is if you're going to get a little better, back at the time, oh, hi. Okay, Mariad. Thank you very much for showing up. Please read the article. It's very interesting if you're interested in how astronomy and quantum mechanics and time all fit together. Okay. So why would we need anything more accurate than 1 second in 1.4 million years? Yeah, it is a good question. And I'm trying to read through the article here as I wing this thing about why. But the idea is that they're experimenting with it. At the time, the reason we use cesium is because it was at the leading edge of our technology. 9 billion times a second is still fairly fast. In fact, our computer speeds are less than that. In fact, I was trying to think of what the best processor can do right now. Actually, some of the best processors are in some of our game things, like the Xbox One has one of the best processors there are. Quantum computers. Now, when we mean quantum, what are we talking about? Because essentially, I'm talking about quantum computer with a cesium clock. Okay, there you go. Ferris has a good suggestion. The faster span, in other words, if we're going to keep up with Moore's law. Here again, what is Moore's law? I hope everybody can hear me because I haven't been typing much. Okay, as long as you can hear me. Absolutely. There you go, Ferris, is that if we're going to start getting out beyond our system here, some of those measurements, the arc measurements and stuff, we're going to need some very, and if we're going to have spacecraft and things, we're going to need some very accurately timed networks. Think of it. Right now we have the internet, which is based on, and this is my topic, I'm teaching this, we're based on the TCP/IP suite of protocols, and those don't work beyond the Earth. So actually there is the same person that invented the internet, Vint Cerf and other people have gotten together to try to figure out how you make an interplanetary network with totally new protocols. Ooh, Ferris, good idea. You're not going to get me on the transporter with a mere 9 billion hertz accuracy. Absolutely. We need a little better resolution than that. Okay, so the JPL, what they're doing is or NPL, excuse me, not JPL, that's over US, NPL is in UK. The National Physics Laboratory is experimenting with strontium and ytterbium. Basically, because we have the technologies now, is that we can use them to make a much more accurate timing system. In fact, here's, I'll let you read that, but the frequency of strontium, for example, is mind-boggling, and I'm not even going to read that number. What do we got? We got billions, trillions, quadrillions. Anybody know what quadrillions are? Quadrillions are what we have with beyond terabytes, trillion, quadrillion. What's it's petabytes. Okay, so petabytes, peta, 444 quadrillion hertz. So basically, one lost second since the Earth began, or accuracy of a second per 5 billion years. And they even have, now you're looking at optical wavelengths here instead of microwave. But we're able to do that now with fiber optics and other things. We're able to time things like that. And particularly with some of the newer communication systems that go at gigahertz speeds, we have technologies that will do that. Now they're even looking at more accurate timepieces with optical clocks, which we're soon going to have optical computers as well. But with optical clocks, we can create timepieces with 1 second in 14 billion years, which is longer than the universe has been around. So, okay, now here's the part about with such insane levels of accuracy, why do we need them? Yeah, I think it's mind-blowing too. Do you know what I find most mind-blowing? One is that people thought of this, okay? I mean, it's amazing enough that there are natural systems out there, and I find that utterly mind-boggling or mind-blowing, but that people actually thought of this, and then, in other words, of the theory, and understood it, and then thought of the engineering that went into it, and then of the practical uses for it. Think of how mind-boggling all that is, as far as, or mind-blowing. That's what I really find the most amazing. That's why I like computer technology and all kinds of other technologies and science. The whole purpose, we're here with the Science Circle. So one of the things is that, so why do we need these accurate systems? Well, what did we say? Okay, here's my teacher coming out. What did we say? We needed a accurate timepiece or universal time, or everybody in one area using the same time back in the 1800s. Why did we say we needed that? Anybody out there? Coordination. Okay, coordination at what? Trains. Okay, so trains wouldn't go crashing into each other. Absolutely. That's pretty important if you're on the train. Okay, so why did we need perhaps quartz watches later? Or, yeah, or more accuracy, okay. For work, okay. For timing. In fact, we could not have Second Life if we didn't have some of these more accurate speeds. The communications just would not work. The streaming of my voice turning into ones and zeros, going lag. Jets, number of things. Computers controlling jets, if you're talking about actual jets. Business itself, communications. All of our modern communications could not work at the speeds they do in the megahertz and gigahertz without extremely good timing systems, because they would also create what's called a crash. Whenever you have communication signals down the same medium without some sort of way to ameliorate that, then and the various ways that we do that, by various channel differences and time differences and stuff like that, then synchronization, absolutely. The synchronization is part of our modern communication systems. So, as I mentioned, one of the things that we use that cesium clocks, and I'm going to give you a quote from the article, is that without the cesium clock, satellite navigation would be impossible, because they use synchronized cesium clocks and able to collectively triangulate your position and work out where you are. Otherwise, the position would be very inaccurate, and it might be, well, you're in Western Europe, okay? So I am now looking at some of the other types of things in the article. Here's one you can take a look at. And 8-bit mentioned businesses. Here we go. I was looking for why you need really good clocks. Here's one of them. What about smart electric grids? Has anybody read about some of the blackouts that people have had, particularly historically on the west coast of the United States? Hey, has Europe had any blackouts? I'm not knowledgeable about the whole world and stuff. Anybody over there live in Europe? Have they had massive blackouts? Yeah, I don't know that I'd read about massive blackouts in Europe. I don't know why. There should be. But basically that's coordinated. But if you're going to have a smart electrical grid, you're going to need a very well-timed grid and controllers on the grid, computers that control it. Because if you say, let's for example, if you have different types of energy, and you have solar energy, and you've got hydroelectric, and you've got I mean, you have wave turbines and all of those sorts of things. Did you? Was there a blackout in Central Europe? Okay. But in any case, if you have all that sort of thing and you're trying to time this and you're doing it on a very large scale with multiple nodes on a grid, you're going to need to have very good timing to be able to keep from having overloads and undercurrent and all of those sorts of things like that. So electric grids. Here we go. Here's a interesting part of that article. If you read a little bit, it basically says that with lulls in the wind and unexpected passing clouds and stuff, all of those can affect solar energy, particularly the more we use alternative energies. And if you don't have very fast controlling of that, then you would have a real problem. Now, another thing, what else goes at very, very quick? Okay, let me read what you have there. Eastern Europe multi-state electrical grid allows peak consumption during hot weather. Okay, there you go. Rolling back and forth. Let's see, about 2 days for nuclear calls. Yeah, the more we have different types of energy sources, and the more they need to be controlled, and the less, particularly like with wind and waves and solar and stuff, where they depend on an unreliable source of wind and waves and sun, then we're going to have timing in order to be able to integrate those sources into the more fuel-burning type. Here's another one. Anybody out there do the stock market or something similar? What did we used to do? Anybody old enough to remember how the stock market used to work? Okay. Well, yeah. Oh, wow. You'd really have to be old to remember that. Ticker tapes were actually what was on the ticker tape was what's called the Baudot code. Here again, there was the Morse code invented in the 1830s, and then the Baudot code, because it had 5 bits per a 5 bits per symbol instead of a variable amount, and the Baudot code was used on the ticker tapes up until the ASCII code was invented in the 1960s, and then Unicode in the 1970s and 80s. Yep, the noisy thing under glass, and the things you used for ticker tape parades and stuff. But in any case, I gave you another reason, is that with the fast machines nowadays, so stocks, you used to have to go through a stockbroker. I remember those days. And then you used to have to go through, in other words, an actual person that would make the stocks down on the floor. And then you had electronic trading. Well, now with modern computers, you can have the big boys, the ones with the supercomputers and stuff, can place thousands of trades per second. And so in the time that you go, whoa, I need to buy this stock, you can have somebody already have bought, sold, bought, sold, bought, sold, bought, sold about thousands of different times. So you're never going to bid those people. So what's the best? This has nothing to do with time and stuff. Well, it does, okay, but it has nothing to do with cesium clocks, etc. But what's a good, for you investors out there, what's a good rule of thumb for any investment, particularly one that makes sense? Is it, do you want to chase the short term, or do you want to go for the long term? Alibaba, yeah. Investing in Alibaba might be interesting. Yeah, first of all, don't invest money you can't afford to lose. That's like, don't lend anything that you don't want to give as a gift to people, and also long term, I think. My strategy has been that if the company's nice and the company's nice to its people and they have a good philosophy and they're ethical, they're probably a good thing to invest in. Okay, so in addition to financial worlds, the other thing is that there are, and there's some very important, speaking of crashes, there's some very important reasons for financials, is that the equivalent of the train crash would be ill-timed stock market trades that could rack up millions of dollars in losses, which then could, the only time when trickle down really works would be that these losses could then trickle down to businesses and cause problems with people and their jobs and all that good stuff like that. Now, in the in the article there is a good little diagram that shows how cesium atoms work, and so why can't we? Let's go back to the sun and the earth. Is a year a year? Has a year always been a year? That is 365.25 days if you use the Gregorian calendar. No. So what's happening to the year? Lost 10 days. When did we lose those? Okay, are you talking about the Julian and Gregorian calendar? Yeah. Actually, let's see, around 1750. 1783? No, 17... Well, now that was 1750 in different parts of Europe. It was actually something like 1563. You can look it up, Gregorian calendar, because it was when Pope Gregory. Let me just throw that in real quick, and then I'll have some questions and stuff. But what Herman's referring to is that, and here's a little calendar thing for you, is that back before most calendars were agrarian. Now, okay, here's a question. In English, the last months of the year are September, October, November, December. Now, anybody out there speaking a Romance language, can you tell me what sept, oct, nov, and des means? What does that refer to? What's sept? Okay, yeah, 7, 8, 9, 10. Absolutely. So why is September, October, November, December 9, 10, 11, 12? Why isn't it 7, 8, 9, 10? Big question. Anybody happen to know? Yeah, exactly. Okay. Well, what's in between? Ooh, there you go. Okay, what's in between? It's got Julius Caesar and Augustus after Augustus Caesar. So why would you have 10 months? Why not 12? What were calendars used for back in the old days? And still. Aha! Okay, yes it does. And actually, some of those were chunked in there because the Senate wanted to be, the Senate actually voted it for it. Like Augustus Caesar, if I recall, didn't want to be emperor, but he was made emperor. Seasons and farming. So you don't need a couple months in the winter because you can't grow and harvest stuff. So who cares about the time there? Basically, you start your clock or you start your calendar in March when there's spring, which is when the first calendars were started in March, including the Roman Empire. And then you don't really need the you just need 10 months when you can grow things and harvest stuff. But Julius Caesar got with his astronomers, I'm trying to tie this into our topic of astroinformatics, and he got with his astronomers and said, okay, we need to get a better calendar going here. And so we're going to have, let's create a 12-month one, and or at least let's create a 12-month one. So he created a 12-month one and alternating 30 and 31 days. And then you got February gets a little short change because the year is not exactly divisible by anything in there. And so you had Julius Caesar and his July of 31 days, and not to be outclassed, you have August with 31 days also. Okay, so that's that. And then his astronomer said, well, okay, but the year is really 365 and a quarter days, so what did they have to do with that calendar in order to have any accuracy at all? Speaking of accuracy, it would have only been, it would have lost a day every 4 years. So what do we do every 4 years with the Gregorian calendar? Leap year! Absolutely. Speaking of which, because of the cesium clock, we have leap seconds. Anybody know what a leap second is? Oh, Ferris. Exactly. That was my next question. We have leap seconds because because the Earth's orbit and stuff is changing, and our rotation of the days are changing. Is every once in a while we have to add or subtract leap seconds. Ooh, okay, Herman. I've got about 8 minutes to extemporaneously speak here, so I will be wrapping it up here shortly. And I also need to run it in about 8 minutes because I have a class in 30 minutes. I got to be ready for it. Okay. So, but let me wrap this up. Is the idea is that okay? So you had the Julian calendar and you had leap years. Now that was good, except that it lost what? And this goes back to what Herman was saying. Is that in 1500 years, how? Yeah, it is. It's pretty poor accuracy. In 1500 years, how much do you lose? And this is why we have the Gregorian calendar today and not the Julian calendar, if you happen to be on that system. There's lots of different calendars in the world. Anybody know? It had to do with the centuries. So in 1500 years, in fact, I just remembered, it was 1582, Pope Gregory, and since they had religious days, they were going, his astronomers were going, Easter is off by about 2 weeks now. And since Easter is actually it's the Sunday after the second full moon after the vernal equinox. And they were going, so which of these 2-week periods do we pick? Because they were almost 2 weeks off. And Pope Gregory goes, well, I don't know, go back to the drawing board, take a look at the Julian calendar, redo it so it works. And they go, okay, Julian calendar works, except what we need to do is we need to do something with the centuries. That is, we're losing a day every 400 years. So what did they do? Here's the question. See if anybody's still awake out there. Was the year 2000 a leap year? Dum, 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 dum. Yes. It was. Okay. Was the year 1900 a leap year? It's divisible by 4. Dum, 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 dum. No, you're right. That's right. Okay, so every 400 years, the centuries are leap years. Every other century is not. So 1600 was because they changed this in 1582. And 2000 was, but 1900 and 1800 and 1700 and 2100 and all that was not. Oh my. Okay, so now at least the calendars were reasonable within a certain period of time, and now we've outstripped them because of the cesium clock, etc., and we have to add seconds and junk. And to make up the time, by the way, Pope Gregory basically said, okay, today is October the 1st, tomorrow is October the 16th, and that's exactly what happened. Except that not everybody adopted these. In Britain, for example, since they were not under the Catholic Church, did not adopt it until the 1700s. So for the U.S., George Washington's, I remember when I was a kid, we used to celebrate George Washington's birthday and Lincoln's birthday, and then they just made it President's Day because George Washington's birthday is 2 different days depending on whether you use the Julian calendar, which he was born under, or the Gregorian calendar, which we have today. Ha. Okay, so in wrapping up what I was saying about the clocks, there are leap seconds. And so let me see if I can throw that up there, and we can do that. It says leap seconds came every 2 years, and then we had 7 years without leap seconds, and then we had every 2.5 years. And there's actually a person who makes up whether we have leap seconds, and that's pretty cool, based on the timing. Okay, so what I have done is that I have given you a quick little thing that's kind of on topic, haha. My students always complain when I go off of, or they don't complain, actually they like it when I do stuff like calendar things and stuff, because that's part of education too, right? Okay, so due to our elliptical orbit, the sun can be off by 16 minutes. Good gracious. And also, of course, depending on where you are, you can have wide time zones. For example, in China, where it may be very Or it used to be in the Soviet Union where they had 8 time zones and it was all on Moscow time. Okay, so now for me, I find timing thing very interesting. Any questions? Any comments? We have everybody here. I don't like it when I'm just the only one talking. So, anybody want to share about what's going on, and we'll wrap it up in about 3 minutes. Oh, thank you. Especially since it was off the cuff, unprepared, but fascinating. Okay, no questions out there, huh? No comments. Any interesting signs? I did mention that one of the things that you need to check out the full lunar eclipse if you happen to be in North America. More bits to store, absolutely. By Swatch, you mean they're still around, the ones that make the watches? How cool. The project of global timing. Oh, you mean like everybody on Universal Time and that's it? Of course, hey, okay, one other time. What's more powerful than Universal Time? Second Lifetime, of course. Except that the time zones. I wonder if we're ever going to do away with daylight savings time or whatever. Hey, tell me what daylight savings time is called in your country or your part of the world. Here we call it daylight savings time, which really doesn't save anything. In the U.S. What do you call it? In Europe, it's called what? Daylight time? A pain in the tail to wake up early. Absolutely. Okay, daylight savings time. Does anybody, since I have one more minute, does anybody know when that got started? Oh, neat. Thank you, Chantel. Summertime, wintertime. Okay, cool. I like it. That actually got started as an idea back in the late 1700s. Yeah, Raja, I'm not quite sure. Legal time. Oh, neat. See, I like to learn. One of the things about Second Life is learning about all of where different things in the world. Okay, real quick, 30-seconder here is that I'm not quite sure. I mean, there's a lot of things contributed to Benjamin Franklin stuff, but it really got started around World War One because they needed to make munitions in the factories and stuff, and they needed to actually save daylight, so they had time to do that. And then they didn't use, in the United States, they didn't use it until World War II, and then World War II, they had daylight savings time the entire war. And then, of course, they had it for a while, and they changed the times, and it was only a few years ago, because I remember that they had to make a fix on the clocks, on the operating systems, so you had the right time on your operating system, is that they would, they changed it so it was longer, I think. So now it goes from like March to November or something. It used to go from April to October. Okay, I have run out of time. Speaking of time, and the magic time around here is exactly 1 hour, which it's now whatever time it is. It's 11 a.m. in Second Life time, so I'm going to quit because I've got a class coming up. But it was, thank you very much. I'm glad everybody was here. It's always wonderful to see everybody. Thank you, Lowry. Thank you, everybody. Okay, you guys take care. Good Second Life and good First Life and all that good stuff. And I'm going to head off to my class. Thank you. I will. We're doing C++ programming, repetition control structures, and all that good stuff. Okay, you too. Thank you very much. And I'm going to step down from the stage, and you guys enjoy yourselves.